Fine, let's start. In 1969, a physicist named Edward Tryon was sitting in a lecture at Columbia University. The speaker paused, and Tryon, apparently unable to stop himself, blurted out loud, "Maybe the universe is a vacuum fluctuation?" Everyone laughed. He was so embarrassed that he never corrected anyone, never explained that he was serious. He just let people think it was a joke and moved on with his life. 4 years later, he wrote it up as a proper scientific paper and submitted it to physical review letters. They rejected it. He sent it to Nature. They didn't just publish it, they made it a feature article. The theory, stripped to its core, is this. In quantum field theory, the vacuum isn't empty. It seethes with energy. Particles pop in and out of existence constantly, borrowing energy from nothing and paying it back almost instantly. Tryon's proposal was simple and slightly unhinged. What if, just once, something borrowed more than it could repay? What if the universe itself is one of those things? A quantum fluctuation that just didn't stop? His explanation for why it happened? Quote, "Our universe is simply one of those things which happen from time to time." That's it. That's the whole answer. The most profound question in human history, why does anything exist at all? And the response is essentially, stuff happens. But here's the thing. Quantum fluctuations don't happen in a void. They happen inside an existing quantum field with existing rules. So Tryon's nothing isn't really nothing. It's a pre-existing something with laws already baked in. Which means the question didn't get answered. It just got pushed back one step, dressed up in a tuxedo, and handed a Nobel Prize nomination. Tryon's idea was called the first serious scientific attempt to describe creation from nothing. Alexander Vilenkin, one of the great cosmologists of the 20th century, said so explicitly. The universe may have started with an awkward moment at a dinner party, and the man responsible was too embarrassed to tell anyone for 4 years. Some things apparently just happen from time to time. Number 9. Dark matter is one of the most persistent mysteries in physics. We know it's there because galaxies rotate in ways that make no sense, unless 80% of all the matter in the universe is completely invisible. We've been looking for it for decades. We have no idea what it is. Here's one possibility that doesn't get nearly enough attention. It's already here. It's been here the whole time. And it didn't come from our universe at all. In 2024, a peer-reviewed paper published in the Journal of Cosmology and Astroparticle Physics proposed the following. Before our Big Bang, there was a contracting universe, a previous universe, collapsing inward. As it contracted, density fluctuations in that collapse would have formed black holes, lots of them. And when the collapse reversed into what we experience as the Big Bang, some of those black holes survived the transition and carried over into our universe. The key detail is the mass range. The black holes formed during that pre-bang contraction would land in what physicists call the asteroid mass window, roughly 10 to the 15 grams up to 10 to the 17 grams. Too big to evaporate through Hawking radiation on any reasonable timescale. Too small to see directly. They wouldn't emit light. They wouldn't interact with anything except through gravity. They'd just drift through the cosmos, invisible, for billions of years. Exactly like dark matter does. And here's where it gets genuinely strange. We're currently building detectors that might find them. LISA, the Laser Interferometer Space Antenna, is a gravitational wave observatory being developed right now. The Einstein Telescope is in planning. The Square Kilometer Array is coming. These instruments are sensitive enough to detect a stochastic background of gravitational waves, a faint, constant hiss of ripples in spacetime produced when those pre-bang black holes formed. If a specific pattern shows up in the data, it wouldn't just be evidence of dark matter, it would be an echo, a sound from before the universe existed. The universe we inherited may be haunted, and the ghost might finally be detectable. Number 8. In 1968, a 26-year-old Italian physicist named Gabriele Veneziano was trying to solve a completely different problem. He was working at CERN, trying to describe how hadrons, the particles inside atomic nuclei, behaved when they collided. He found a mathematical formula that fit the data beautifully. He published it. Moved on. What he didn't realize was that he had just accidentally invented string theory. The formula described particles not as points but as tiny vibrating strings. It took years for other physicists to understand what Veneziano had actually found. By the time the implications were fully clear, string theory had grown into the most ambitious framework in the history of physics, an attempt to unify all forces, all particles, all of reality into a single coherent mathematical structure. And then, 23 years after that original paper, Veneziano was working with Maurizio Gasparini at CERN. They were studying the duality symmetries that string theory implies mathematical relationships that connect very large scales to very small ones, high energies to low ones. And they found something unexpected. String theory doesn't just describe our universe after the Big Bang. It implies a phase before it. The scenario they developed is called the pre-Big Bang scenario. Before our universe existed, there was a long, cold, almost featureless phase of string vacuum, nearly empty, very low curvature, very low energy. The universe wasn't hot and dense. It was barely there. And then, driven by a field called the dilaton, a companion particle that string theory requires this near-nothing state became gravitationally unstable. It collapsed and heated and ignited into what we experience as the Big Bang. The theory comes with a testable prediction. The pre-bang phase would have generated a distinctive pattern of gravitational waves, a stochastic background with a specific spectrum. Current and future gravitational wave detectors could, in principle, detect it. We haven't yet, but we're getting closer. The formula Veneziano wrote to describe particle collisions in a lab contained, buried inside its mathematics, a description of what the universe was doing before it existed. He had no idea. Nobody did for over 2 decades. Sometimes the universe hides its autobiography inside someone else's homework. Number 7. Picture 2 enormous sheets of paper floating in a room with 5 dimensions instead of 3. Each sheet is a universe. Each contains galaxies, stars, the whole story. They can't see each other. They can't interact except through gravity, which bleeds across the gap between them. For a very long time, maybe an eternity, they drift in silence. Then they drift toward each other. They collide. And the energy released from that collision is the Big Bang. This is the ekpyrotic model, proposed in 2001 by Justin Corey, Bert Overoot, Paul Steinhardt, and Neil Turok. The name comes from the ancient Greek word ekpyrosis, the Stoic philosophical concept of the universe being periodically consumed by cosmic fire and reborn from the ashes. The Stoics believed the universe lived in eternal cycles of destruction and renewal. Steinhardt borrowed the word deliberately. The sheets in this model are 3-dimensional membranes, brains embedded in a 5-dimensional space. Our universe is one brain. There is another, parallel brain just beyond what we can see or detect, separated from us by a gap in the 5th dimension. Light can't cross that gap. Matter can't. Only gravity can reach across it. Before our Big Bang, the model says, there wasn't a hot, dense singularity. There was cold, quiet, almost nothing. 2 membranes slowly drifting toward each other through a higher dimension until, inevitably, they touched. The collision imparted energy. That energy became our universe. But here's the thing. Paul Steinhardt was one of the original architects of cosmic inflation, the dominant theory of the early universe, the framework that explains the large-scale structure of the cosmos that we actually observe. He helped build it, and then he looked at it carefully, decided it had fundamental problems, and spent years constructing a rival that doesn't need inflation at all. The man who helped design the reigning theory of cosmic origins concluded it was wrong and started over. That's either the most scientifically rigorous thing imaginable or a warning sign. Possibly both. There was another universe out there, close enough to touch us through a dimension we can't enter, and eventually, it did. Number 6. The Big Bang isn't really named after a bang. It's named after a sneer. Fred Hoyle, the British astronomer who spent most of his career arguing that the universe had always existed and always would once refer dismissively to the competing theory as the Big Bang, he meant it as a jab. It stuck anyway. Hoyle's own theory, the steady-state model, was eventually abandoned. The Big Bang won. And now we spend a lot of time asking what happened before it. Loop quantum cosmology has a specific answer, a contracting answer, a previous universe. Here's the idea. In standard general relativity, if you wind the clock back on the universe, density increases without limit until you hit a singularity, a point where the equations break down and physics stops. That's the Big Bang. It's a wall. You can't go further. But loop quantum gravity, one of the leading approaches to unifying quantum mechanics with general relativity, says space is not continuous. It's made of discrete units, like pixels but for the fabric of reality. And discrete things have a minimum size. You can't compress a pixel to 0. You can't compress space to 0 either. So when a contracting universe approaches that minimum scale, quantum effects generate a repulsive force, not from any new particle or exotic field, just from the fundamental graininess of space itself. The collapse reverses. The universe bounces. What we call the Big Bang in this picture is actually the moment of maximum compression in a much longer story. A previous universe contracted for billions of years, hit the floor of what's physically possible, and rebounded into the expansion we're currently living through. The density at that bounce point is calculable. Approximately 0.41 times the Planck density, roughly 5 times 10 to the 96 kilograms per cubic meter. That's a number so large it requires a moment of silence. For comparison, a neutron star, one of the densest objects we know of, sits at about 5 times 10 to the 17th kilograms per cubic meter. The bounce density is 79 orders of magnitude higher. And the pre-bounce universe is deterministic. Its properties can, in principle, be calculated and traced backward. The pre-bang universe left potential fingerprints in the cosmic microwave background, the faint afterglow of our universe's early heat. If future telescopes, like the CMB, S4 experiment, reach sufficient sensitivity, those fingerprints might be readable. This is one of the very few theories on this list that could actually be falsified by observation, which either makes it the most trustworthy entry here or the most vulnerable. For a moment, consider that every time you look at the night sky, you might be looking at the afterimage of something that died and was reborn. The universe didn't start, it fell and got back up. Number 5. Roger Penrose won the Nobel Prize in Physics in 2020. The prize was for his 1965 proof that black hole singularities necessarily form in general relativity, a result so fundamental it reshaped how physicists think about gravity. He is one of the most mathematically gifted people who has ever lived. He is also, at least in the eyes of some colleagues, currently wrong about something very specific. His theory is called conformal cyclic cosmology. The idea is elegant and strange in equal measure. Our universe, according to this model, will expand forever. Stars will burn out, black holes will slowly devour everything. And then, over timescales so enormous they make the current age of the universe look like a rounding error, even the black holes evaporate through Hawking radiation. What's left is a universe containing only massless particles, photons, perhaps gravitons drifting through infinite expanding space. Here's the key. Massless particles don't experience time the way massive particles do. They can't carry a clock. For a photon, the beginning and end of its journey are simultaneous. And in a universe containing only massless particles, the concept of scale, how big or small things are, becomes meaningless. Distances can't be compared. There's nothing to compare them with. Penrose realized that this creates a mathematical equivalence. The infinitely large, cold, empty end of one universe and the infinitely dense, hot, small beginning of the next one are, in terms of their conformal geometry, identical. The end of one aeon and the beginning of the next are the same moment, seen from different sides. The cycle repeats, endlessly. No beginning, no end. Just aeons stacked inside each other, each one generated by the death of the last. And before our Big Bang was the final heat death of a previous universe. Its black holes collided. Those collisions sent ripples through the fabric of space-time gravitational waves that survived the transition between aeons and embedded themselves in the oldest light we can see, our cosmic microwave background. In 2010, Penrose and his colleague Vahe Gurzadyan at the Yerevan Physics Institute in Armenia claimed they found them. Faint rings of unusually uniform temperature scattered through the CMB circular imprints, Penrose argued, from the gravitational wave signatures of supermassive black hole mergers in the universe before ours. Multiple independent teams reanalyzed the data. They found nothing statistically significant. Penrose disagrees. The debate is unresolved. But here's the deeper problem. For conformal cyclic cosmology to work, every massive particle in the universe, every proton, every electron must eventually lose its mass or decay. Proton decay has never been observed. Not once. Experiments have been running for decades looking for it. Nothing. Penrose is a Nobel laureate staring at the oldest light in the universe, claiming to see the fossil of a universe that died before ours was born. His math is serious. His critics are serious. The question is completely open. Somewhere in the faint static of the cosmic microwave background, there might be a ghost. We just can't agree on whether we're seeing it. Number 4. Let's be very precise about what nothing means. Not a dark room. Not empty space. Not a vacuum filled with quantum fields. Not the absence of matter. None of that. Something more fundamental. A state with no space, no time, no geometry of any kind, no fields in which quantum fluctuations could even occur. A state where the word before doesn't apply because there's no time for anything to be before. That's what Alexander Vilenkin was working with in 1982. Vilenkin is a theoretical cosmologist at Tufts University. His paper is called Creation of Universes from Nothing. It's not a metaphor, it's a calculation. His argument uses quantum tunneling, a real, experimentally confirmed phenomenon. In quantum mechanics, particles can tunnel through energy barriers that classical physics says are impenetrable. A particle sits on one side of a barrier with insufficient energy to climb over it, and yet somehow it appears on the other side. No violation of physics, just probability. The barrier isn't a wall, it's a hill, and quantum mechanics allows a small but non-zero chance of passing through it. Vilenkin proposed that the universe did this, that it tunneled not through a barrier in space, but through the barrier of non-existence itself. On one side, nothing. On the other side, a small, closed universe, geometrically complete, about to inflate. The calculation works. The math is internally consistent. The universe could, with some non-zero quantum probability, simply nucleate from absolute nothing. But here's the thing that Vilenkin himself is careful about. The tunneling still requires quantum laws to operate. Probability amplitudes have to be defined. Wave functions have to exist. And quantum laws are not nothing, they're something. A set of rules hovering in the void with no obvious origin, ready to be applied the moment they're needed. So, where do the laws come from? Vilenkin has no answer. He says this openly. The laws themselves remain unexplained. The mystery doesn't disappear. It retreats. You follow the question back as far as it can go, and at the very edge, where physics runs out, there's still something rather than nothing. Just something smaller, something more abstract, something that looks from a certain angle suspiciously like mathematics existing independently of any universe to contain it. The universe didn't come from nowhere. It came from the rules. And the rules don't have a return address. Number 3. You're inside a black hole right now. Not a small one, not a dramatic one, with a visible event horizon. The biggest kind, the kind so large that if you crossed its event horizon, you wouldn't feel anything unusual. Space would look the same, the stars would still be there. You'd have no way of knowing, and you couldn't get out. This is the theory proposed by Lee Smolin in 1992. Every black hole, in his model, is a doorway. When a star collapses past the point of no return, and a singularity begins to form, something else happens first. The collapsing matter reaches such extraordinary density that a new universe buds off inside the event horizon, not in our space, in a new space, causally disconnected from ours. An entire cosmos, inflating and expanding and eventually forming stars and planets and possibly life, all inside what looks, from our perspective, like a singularity. In 2010, Nikodem Poplavsky at Indiana University worked out a specific physical mechanism for this. He used a version of general relativity called the Einstein-Cartangent-Sayama-Kibble theory, which accounts for something standard relativity ignores, the intrinsic spin of particles. At normal densities, the effect of spin on spacetime is completely negligible. But at densities above roughly 10 to the 50th kilograms per cubic meter, it generates a repulsive force torsion powerful enough to halt gravitational collapse before a singularity forms and bounce the infalling matter into expansion. He calculated the mass of the black hole that could have spawned a universe the size of ours, approximately 1,000 solar masses, what's called an intermediate mass black hole, not the biggest kind, not a stellar remnant, something in between, something that plausibly exists in our parent universe, if there is one. His work was listed among the top 10 scientific discoveries of 2010 by both National Geographic and Science magazine. But Smolin's version of the idea goes further. He called it cosmological natural selection. The proposal is this: each daughter universe inherits slightly varied physical constants from its parent. Universes that produce lots of black holes produce lots of daughter universes. Over many generations, the universes that survive and proliferate are the ones whose physics is optimized for black hole production. Look at our universe. The constants of nature, the strength of gravity, the masses of particles, the value of the cosmological constant appear fine-tuned in ways that seem almost suspicious. Fine-tuned for complexity, for stars, for chemistry, for life. But also, almost incidentally, for black holes. Lots of them. In cosmological natural selection, that's not a coincidence. That's the selection pressure. Our universe is good at making black holes because universes that weren't good at making black holes didn't survive long enough to produce us. There's just one problem. We can never look out. The event horizon of the black hole that contains us is the boundary of our observable reality. Whatever universe exists beyond it, the parent universe, the collapsing star that started all this, is permanently and absolutely inaccessible. There is no experiment, no telescope, no theory that can reach through that wall. We are inside a story we can never read from the outside. And somewhere in the parent universe, from the outside, we look like nothing at all. Number 2. The universe should be symmetric. That's one of the deep assumptions embedded in the laws of physics, that if you flip every charge, mirror every spatial direction, and reverse time, the fundamental behavior of particles and forces should look identical. This is called CPT symmetry: charge, parity, time. But our universe isn't symmetric. Time only runs forward. There's vastly more matter than antimatter. Everything we can see exists on one side of a ledger that should, by the rules of physics, be perfectly balanced. The other side is missing. In 2018, Latham Boyle, Kieran Finn, and Neil Turok, working at the Perimeter Institute for Theoretical Physics in Waterloo, Canada, published a paper that takes CPT symmetry seriously in the most literal possible way. Not as a property of individual particle interactions, as a property of the entire universe across all of time. Their proposal: the Big Bang is a mirror. On one side is our universe matter-dominated, expanding, time running forward. On the other side is an anti-universe, antimatter-dominated, also expanding outward from the Big Bang, but in the direction of our past, time running in the opposite direction. Together, the two universes form a single CPT symmetric whole. Each one is the exact mirror image of the other. From inside either universe, time appears to run only one direction. The asymmetry you perceive is real, it's just that the universe as a total system is balanced. You're living in one half of a pair. The model requires no cosmic inflation, no exotic new particles, no fine-tuning. It takes the existing laws of physics and applies a symmetry they already possess to the universe as a whole, and several deep problems dissolve. Dark matter, for instance. The CPT symmetric model naturally produces large quantities of sterile neutrinos, right-handed neutrinos that don't interact with the weak force. Specifically 3 of them, at calculable mass ratios. These sterile neutrinos are a candidate for dark matter. Turok described them as being radiated from the Big Bang, like Hawking radiation from a black hole, naturally, inevitably, without any additional assumptions. This is testable. The Euclid Space Telescope launched in 2023. The Vera C. Rubin Observatory is beginning operations. These instruments are conducting galaxy surveys sensitive enough to distinguish between this model and the standard inflation scenario within the next several years. Not decades, years. But the deeper implication is stranger than the physics. If this model is right, then the question, what existed before the Big Bang, has a very specific answer. Before our Big Bang was another universe, not a previous one in time, a simultaneous one in a mirrored direction. Our universe and its twin are not sequential. They exist together, symmetrically, with the Big Bang as the joint origin point, the center of a structure that extends both forward and backward in what we call time. You've been asking what came before. The answer might be, nothing came before. There is no before. There's just the other side. And somewhere, in a universe that runs opposite to ours, every particle is the antimatter reflection of its counterpart here. Every galaxy has a ghost. Every moment in our future corresponds to a moment in their past. They will never know we exist. We will never know they exist. But together, we make something whole. Number 1, here is the question we've been circling for this entire video. What existed before the Big Bang? And here, finally, is the most unsettling possible answer. The question doesn't work. Not, we don't know yet. Not, the answer is complicated. The question itself may be malformed, like asking what's heavier, blue or Wednesday. The grammar is intact, the meaning isn't. In 1983, Stephen Hawking and James Hartle published a paper called Wave Function of the Universe. It proposed something that sounds simple and contains multitudes. When you approach the Big Bang and the density of the universe becomes extreme when you enter the regime where quantum gravity matters, time doesn't end. It doesn't begin either. It changes. In quantum gravity, at Planck scale densities, the distinction between time and space breaks down. Time, which you normally think of as the dimension you move through rather than across, begins to behave like a spatial dimension. It doesn't point forward and backward anymore. It points in all directions equally. Hawking used an analogy, Imagine traveling south from anywhere on Earth. You keep going south, the temperature drops, the landscape changes, and then you reach the South Pole. And at the South Pole, the direction south ceases to mean anything. There is no south of the South Pole. Not because there's a wall there, not because you've hit a boundary, because the geometry has changed and the direction no longer applies. Going backward in time toward the Big Bang is like traveling south. At some point, you reach a region where before no longer applies. Not because something blocks you, because the concept stops being geometrically valid. The universe, on this view, has no beginning. Not in the way a marathon has a starting line. It just tapers. The past becomes a direction that smoothly ceases to be meaningful. There is nothing before the Big Bang, because before requires time, and time, as you approach the origin, gradually stops being time. Hawking put it plainly. At the Pontifical Academy of Sciences in 2016, one of his final public statements on the subject. Asking what came before the Big Bang is meaningless, he said, because there is no notion of time available to refer to. It would be like asking what lies south of the South Pole. This is, in one sense, the most satisfying theory on this list. It closes the loop. It explains why we keep failing to find a before, not because we're not clever enough, but because there's nothing there to find. But here's the thing. Hawking's biographer, Kitty Ferguson, noted that the no-boundary proposal is actually less accepted among physicists than Hawking's most famous contribution, Hawking radiation. It's not the consensus. It's a proposal, a beautiful one, a serious one, but contested. In 2017 and 2018, a team that included Neil Turok, who also appears earlier in this video, formally challenged the mathematics of the no-boundary proposal. Using a more rigorous treatment of the path integrals involved, they argued the proposal actually predicts a universe that is wildly fluctuating and inhomogeneous, not the smooth, large, ordered universe we inhabit. Their conclusion: the math doesn't do what Hawking said it does. Hawking was already gravely ill. He died in March of 2018. The debate was never fully resolved. It remains open. So here is where we actually are. One of the greatest minds in the history of physics proposed that the question of what came before the Big Bang is like asking what's south of the South Pole. Not wrong, just geometrically incoherent. And the challenge to that proposal died, unanswered, in the same year as the man who made it. We don't know what came before the Big Bang. We don't know if before even applies. We don't know if the universe tunneled from nothing, bounced from a predecessor, was born inside a black hole, is one half of a mirror pair, is a pocket in an eternal self-reproducing foam, or is simply the fire left over from two other universes colliding in a dimension we can't enter. What we do know is this. Every single one of those theories was proposed by serious physicists, published in serious journals, and is still being actively argued over. None of them is obviously wrong. None of them is obviously right. We are a species that learned to walk upright only about 3 million years ago, developed writing only about 5,000 years ago, and has been doing modern physics for roughly 400 years. And we are attempting to describe what reality was doing before it existed. Every theory in this video assumes something. That quantum laws existed before the universe. That time is a road with a direction. That cause and effect apply at scales we've never accessed. That the mathematics we invented on this small, warm planet accurately describes conditions so extreme they are, by definition, beyond anything we can measure. Maybe time doesn't have a beginning. Maybe the question is wrong. Maybe the answer is stranger than any of the theories we've built so far. Maybe, and this is the one that stays with me, the universe isn't something that started. It's something that simply is, stretching in all directions, including the one we call the past, without an origin and without an end. And the question what came before is us, doing what humans do, looking at something vast and ancient and incomprehensible, and asking where it keeps its receipts. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.